Okay, G, so you've convinced me sort of that sampling distributions are usually normal unless you have really small samples. But what about the center and the spread of the sampling distribution? What can you say about that?
Okay, so we've been looking a lot at just the overall shape of these distributions, but now we're going to turn our attentions to these little numbers right here, these summaries of these distributions. We're going to look particularly at the mean, the center, and standard deviation as a measure of how spread out this distribution is, right? So here notice that our mean is 16 and our standard deviation is 5. And I'm going to go ahead and create a sampling distribution of means for n equals 5 and n equals 25. Now, for both of these, we should expect them to be fairly normal looking. That's what we've learned so far from a parent population that's normal. But notice that even though my sampling distribution is made up of n equals 5, so small samples or larger samples, the mean in both of these cases is pretty close to the mean of the population, right? So the mean in this case is 15.99, and there's like a little blue tick mark right there. And the mean of this sampling distribution of means is 16.01, pretty close to 16, right? But here's another thing you notice right off the bat, right? This population, these data points vary much more than the means do, right? And the means vary even less when you have a larger sample size, right? And so these means are very tightly clustered around the true mean of the population, whereas these samples are a little bit more loosely clustered, right? But that's part of why we use the mean so much. The mean is a pretty good, a mean of any sample is a pretty good indication of the mean of the population, especially when your mean comes from a sample that's fairly large. So that's good for the parent population that's normal, but let's try something else. Let's try it even with something that looks a little crazy, something that we make up, right? So let's make up a distribution, and we're going to just draw in a distribution, and you could try it yourself and draw in all kinds of crazy distributions, whatever you think looks good to you, right? So look at this distribution, and this little application will calculate directly for you. The mean of this parent population is 19.47, and the standard deviation is quite large, right? So the standard deviation on average, it's each data point is about 7 units away from that mean of 19, right? So that's what it is. So if our observations are true, then we should expect these sampling distributions to be much more clustered together. The means should be less variable than the actual individuals in the population. And we maybe expect this one to be a lot more tightly clustered together than the n equals 5 sampling distribution. So let's try it with 10,000 samples, and let's see. So we definitely see that the spread of this, so we expect the standard deviation to be bigger than this one, and that's true. This is about 3.19 and this is 1.41, right? And so here we see that these means are on average much more tightly clustered in, and these means are a little bit looser. But in both of these cases, both sampling distributions of means the means are much more tightly clustered together than the actual individuals in our population. Also, even though this came from a pretty weird looking distribution, the mean of the sampling distribution of n equals 5, 19.5, is pretty close to 19.47. And the mean of this one too is 19.49, right? Pretty good, right? And so we're seeing that the mean seems pretty robust. The mean of the sampling distribution of means doesn't seem to care that much about the shape of the parent population, nor the sample size. The mean of these sampling distributions seem to be pretty good, no matter what.